We're now going to look at some simple but reasonably practical applications of least squares. We're going to see a lot more before the course is over, but just to give you some very simple ones. Obviously, these are simplified, and you can be much more sophisticated in these applications. It's just to give you a flavor. Okay, so the first one concerns advertising purchases. Okay, so the way that works is we have M demographics groups we want to advertise to. So here's one, for example, 18 to 22-year-old, college students. There's one demographic. Here's another one, women, 35 to 40 years old. There's another demographic. But you have a bunch of these, and I think there's standards for these different demographic groups. Okay, M might be tens, could be hundreds, I don't know, whatever, it depends. All right, so each of those groups you want to advertise to. And what I do is I have a target, V desired, V superscript des, which is for desired. That's an M vector of target views or an impression. Now, a view or an impression, and by the way, you don't need to know this. The class is not about advertising, obviously. So it's just an example. So don't worry if you don't know what in fact, it's not like I know that much about this either. So fine. So a view or impression is defined as a moment when a person in the target group sees an ad or receives an offer or anything like that. I mean, it could be on a website. It could be anything. It covers a lot of things. So that's called a view or impression. Okay, and so what this is you've got a vector here of the target views or impressions. In other words, you'd say, I want 18 to 20-year-old college students. I would like to deliver 50,000 impressions to them, right, in my advertising campaign. Okay, so I have an N vector, S, and that's going to give me, it's going to give me my spending in dollars on N advertising channels. Okay, now an advertising channel is, it's just what it sounds like. It's something where you pay them and they serve impressions, right? So sometimes it's a publisher, could be on a search engine, could be all sorts of stuff. Could even be traditional stuff like, magazine ads or something. I mean, it could be, right? So those are so-called advertising channels. Okay, and then what you have is a matrix M by N R, and it's called the reach matrix. And what it does is it's going to tell you for each of your channels how many, for let's say $1 that you spend on each channel, it tells you actually how many impressions you get in your M demographics groups. Okay, so let's see. Rij is the number of views per dollar spent. Maybe in, let's say, 1,000 views per dollar. I don't know, whatever. So a view costs you whatever that is, a hundredth of a cent, or tenth of a cent. Sorry, there you go. Okay, so it's how many, if you spend $1 in that channel, you're going to get 1,000 views, right? So if you spend $100, you get whatever that is, 100,000. Okay, so Rij is the number of views per dollar spent, and so that's an interesting matrix, right? We can take a look at it. It looks like this, and as I would recommend you do always when we get into applications, go slow, sit down, and ask yourself. You should always ask yourself the following: what does a row of that matrix mean? And what does a column? So let's answer that question. So what does the third row of this matrix mean? Well, it's a row vector. Its width is N. N is the number of advertising channels I have. So this is the third demographic group. Let's suppose it's 18 to 22-year-old college students. Then what this says is it will tell me for all of my channels, every time I spend $1 on that advertising channel, it tells you how many people in this group are actually gonna get an impression. Okay, so I could ask you this: how would I find, if I only wanted to target 18 to 22-year-old college students, right? If that's all I ever wanted to do, then it's really simple. I would scan across this row and I would find the largest entry, because that is the one that is most efficient. For $1, I will get the most 18 to 22-year-olds. Okay, so that would not be, for example, advertising in like AARP or something like that. That's American Association of Retired Persons. That would be a very bad choice. And presumably, there's a shockingly small number there, meaning that for every dollar you spend advertising with them, guess what? You're not hitting college students. Okay, so all right. Let's think about, let's say, the fourth column in this matrix. That's also super interesting. So the fourth column is associated with the fourth advertising channel, right? Something like that. I don't know what it is. So that's the fourth column. And what it does is it tells me this. It says that when I spend $1 on the fourth advertising channel, if I read down this vector, it tells me how many people in each demographic group I hit. That's what it is, right? So you could ask things like this. Hey, for advertising channel number 4, which group gets the most impressions? And we could look it up and find out who it is, right? You just scan down here and you'd say, oh, it's demographic group number 22. And then you'd have to look up what demographic group 22 is, right? So that's the idea. Okay, so, and by the way, I recommend doing this like always, right? Because after a while, we kind of get, this matrices flying around, but some of them are going to be huge. And it's very important you sit down and actually try to understand what each of these, what they mean. Okay, all right, so this is the matrix R. Now, if I multiply R times S, the reach matrix times the spending vector, then I get a vector, which is V. And V is actually the views I get. So if I say I'm going to spend $1, on these magazine ads, and I'm going to spend, $2 with Google with these search words, and I'm going to do that and blah, 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 and I go on and on. Okay, then what's going to happen is that's S, and then I multiply by R, and matrix vector multiplication here converts the amount you spend on each of the channels into the number of impressions you get in every one of the demographic groups. Okay, so that's the idea. And what we would like is V to be some target one, right? Because some people in the analytics department said, okay, for our product, here are the people who are going to buy our product. It's these people. Please target them. Okay. Okay. So this is the idea, and we can do this. We can look at when you choose an S here, RS or V desired minus RS divided by square root M, because this has a length of M, a dimension of M. That is the RMS deviation from the desired views. Okay, and we can use least squares spending. So that would be we get as close as we can. I'm assuming here that the reach matrix is tall and has linearly independent columns. Actually, it's super interesting to see what it means for entry, if that were false, right? Or in simple cases, right? Like what it'd actually be kind of interesting. If this has dependent columns R, it means that one column is a linear combination of the others. That's interesting because what that means is that you don't need that advertising channel because you can replicate it with a linear combination of other channels. So it all kind of makes sense. Even the linear independence here makes sense. Okay, now we'll use least squares spending, and that says decide how much money to spend in each channel to get as close as possible as measured by the norm or norm squared or RMS value to this target views or impressions, right? And so that's going to be this thing. Now, at this point, I do have to admit something to you, just out of honesty, that when you do this, there's no reason to believe that S hat is going to have positive entries. And that's going to be very awkward because it's going to say you should go, let's say you're trying to hit college students, it's going to say, you know what? Not only should you not spend on, AARP magazine, you should actually spend a negative amount. Now, that doesn't make any sense and you're not allowed to do that. So, however, I'm just admitting that that's the case. I can also tell you this, that if you fast forward a couple of classes, you will find out that you can actually ensure that the S's are non-negative. So it's not a problem. It's just not something that's in scope of this course and this book. Okay, so that's it. Let's look at an example. It's very baby example just to give you a rough idea. So I have 10 demographic groups and I have 3 advertising channels. My target views vector is this, I want to hit, let's say 1,000, 1,000, 1,000. Now I believe that the views was in thousands of views. So basically, I have 10 demographic groups, and I would like 1,000,000 people in each group to see my ad or whatever it is. Okay, so that's the idea, and that's it. It didn't have to be, but it's a simple way to do it. So we do this. Now, when you actually work out what is R hat, R dagger times V desired, you get this, and it says that's how much you should spend. It's kind of cool, right? Because it says mostly you should put a lot of money into the third channel, much less into the first, and a little bit into the second, or something like that. I mean, you can, however you want to describe that vector, but it tells you what to do. So let's actually, here's the matrix, and it's plotted this way. Let me explain what it is. These are the groups, and you can see channel 1, channel 2, and channel 3 here. And let's focus on channel 2. So channel 2 says that for $1, if you spend on channel 2, here's what you get. You're gonna get, I don't know, in demographic group 1, you're gonna hit like 1.9. That's 1.9. That's 1,900 impressions. We're doing really well on demographic 2. So I don't know what channel 2 is, right, or demographic 2, but I tell you this, the people in demographic 2 are reading, watching, or whatever, or being exposed to channel 2, clearly. Now, you're doing pretty badly out here, demographic 10. So every dollar you spend on channel 2, basically almost no one in demographic group 10 is seeing it. Okay, so this is the idea. So this will give you, this is actually a pictorial picture of the matrix R. Okay, now, when I actually spend this amount here, I get, and remember my target was 1,000. So what I wanted was all 10 of these to be lined up at 1,000. Well, here's what happens. There's a drum roll, and it turns out this is what I achieved. By this spending vector, I get this. And it's really pretty cool, right? What I would love is for all of these gray bars to be right at 1,000. That'd mean I nailed it. It would mean like, you go back to whoever it was who gave you V desired and said, I got a spending plan and we nail it. That's it. That'd be perfect, right? I mean, the whole thing is silly, right? Because, who knows how many people actually buy it. That's another story. Fine. And here's what you can see. Out of the 10, we come in a little bit low. I mean, here's like 800 and something, and here we come up a little bit high. It's maybe 1,200, right? But, pretty much all around, we're getting, we're between 800 and 1,200, usually, right? And for some of them, we're really close. Like, here you go. Demographic 10, we pretty much nailed. So, that's the idea. So this is just an example of how you would use least squares in practice. And it's kind of clear that it's a little bit obvious. Now, this one was silly because it's 3 channels. There's just three variables. So you honestly could have tuned it by hand. But let's remember that the exact same code would work if there were 500 channels and 10,000 groups. Okay, so it would just work perfectly. Let's suppose the groups were broken up by region. So if you said, well, in the North Bay, 18 to 22-year-olds, blah, 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 all this kind of stuff, you could easily end up with 10,000 groups, and you could easily have hundreds and hundreds of channels, and the exact same code. By the way, the code is basically S equals R / V desired. I'll just write the code out for you right here. It's S hat equals R / V desired. One thing I should be very clear about. R is not the R from the QR factorization. R is the reach matrix. That's why it's got the name R. Okay, so in which case, by the way, if there were 500 advertising channels and 10,000 groups, you could not do this by hand. I mean, you might attempt to, but it would be really pretty stupid, frankly, because you can just do it and get a beautiful spending thing like that. Okay, good. So that's our first example. Our second one involves illumination. So what it is I have a region that I want to illuminate, and I have lights that are up above us, and they're in weird locations. It's not on a regular grid. So here's light number 1 is right here, and lamp number 1, and it's 4 meters above the floor. Okay. Here's lamp number 2, and it's 3.5 meters above the floor. And here is lamp 10, and it's 4.5 meters above the floor. Now, you can picture what happens, right? That when you're higher, above the floor, it means that when you turn that light on, it's going to cast a wider pattern of light. It'll be weaker, but it'll actually cast a wider a pattern of illumination. Okay, and so there you go. That's what it is. So Aij is going to be the illumination in region I. So I divide up my ground into regions here, which is there's 625 regions because I make them like pixels of 25 by 25. So I have these are so I have 625 pixels or regions, right? And the illumination in that, I'm going to have A be a matrix where Aij is the illumination in region I if lamp J is on with power 1 and all other lamps are off. Okay, so you go into this thing and you do the following. You turn lamp J on to power 1, everybody else off. So there's a single sole light, spreading light down, and you'll get a pattern. And look, you know what it's going to look like. It's going to be kind of circular, and it's going to be brightest right under the light, and it's going to tail off and stuff like that. I believe the data for this is done using with a very simple standard inverse square model. So, the farther you are from the light source, the illumination goes down like this. You don't even need to know that. It's not relevant. Anyway, this is how you do it. Oh, and you'll also see that when I said this experiment of heating up lamp J to power 1 and turning all the others off, you should by now be associating that with it. That's a unit vector. That's what that is. And that gives a column of A. So let's just talk about A for a minute. So A looks like this, right? And a column of A actually gives you the illumination pattern of that particular lamp because a column is associated with a lamp, right? So presumably all the numbers are positive, right? Presumably the largest number in here occurs at a pixel which is right under the lamp, the source, right? But other than that, they're all over. Some are big, some are small. If you're very far away, it's very small. Now a row is also super interesting. A row actually tells you corresponds to a pixel, like that guy right there. And the row tells you that for all the lamps, how much per watt do they illuminate you? Okay, and so in this case, we would assume that these guys are close. They're close, but they're also kind of high, right? Relatively high, relatively speaking. So we would assume that the entry in this row, the 4th entry and the 8th entry would be pretty big. So would the 5th entry, by the way, and maybe the 9th. And probably the smallest entry would be the 3rd entry in that row, right? So you can think of it this way. A row tells you the lighting efficiency of all of your lamps for a particular pixel or region. Okay, that's it. And I have, if I multiply A by X, that means I add the power level. Each lamp is spraying light down, and I just add up the illumination levels. And AX gives me a vector, a 625 vector in this particular example. It's M is 625, and basically it says that this is the illumination pattern you get if you use power X. Okay, and then I have a target illumination level of BI, right? So maybe, who knows? I just have some target I would like. It could just be uniform. That's simple, right? But it doesn't have to be. You could, for example, say I want a lighting gradient, meaning I want it to very linearly or affinely across this region. Okay. Okay. So here we are. What we're going to do is we are going to attempt to achieve uniform illumination. Okay. Now, we've arranged everything that if you just turn all the lamps to power 1, that's X equals 1, this is the illumination pattern. And red means brighter, blue means darker. And if you do that, you get something like this. Hardly surprising, right? What you see is that this is very well illuminated because they're in view of a lot of lights, and you turn them all on to one unit, then it's going to be overlit. And then over here, like in the corner, it's pretty dark. It's dark because, well, there's not that many lights near it. Okay. And what we have here is, this is the histogram. So there's a total of 625, regions or pixels. And this tells you what the illumination is. And you can see they kind of center around 1. That's cool. This is our target, right? We want everything to be an illumination of 1. But you can see, I mean, presumably the blue here is, that's over there. It's pretty, your illumination is down to 0.5. Some places have an illumination that's up at like 1.6, and that's presumably the red places. Okay, so this is the picture. Now we do least squares. We just simply do backslash in code, or we form the least squares one. By the way, the same comment I made about the last example holds here. That is to say that when you solve this problem, you could end up with negative lamp powers, which, by the way, would give you stunningly good lighting. There is no such thing. You can't do that. But we'll skip that and pretend it doesn't. It did not happen in this case. And what this does is it tells you what to do with your lights, and it's actually pretty cool. I don't have that here, but what it says is this light should be a little bit brighter than 1. And these guys, you really got to back off from 1, right? And the reason you back off from them is because they're in an area with a lot of lights and they don't need to be that bright, okay? So you're just sort of compensating for all that. I'm anthropomorphizing how this works, right? So that's actually going to be an important part in least squares, is you're going to be able to do all sorts of crazy stuff, and people would say, how did you do that? What happened, or something? And then you can tell a story. And sometimes it's better to say, well, to make up a story. Now, the truth is, what you really did is you just did least squares. But okay. Now, when you do that, visually, you can just see that that's a whole lot better than the one above, right? In the one above, you see hot spot in the middle and cooler spots. Here, well, you can't avoid some cool spots like this, but the hot spots are kind of gone. And sure enough, look at this. If that's our target, you can see that, actually, a whole lot of that region is within, between 0.85 and 1.15. So you went from these things here where the errors were, easily 25% down to one where they're like 10%. It's pretty good. Okay, so again, this is just an example, but it should start you thinking about, applications of least squares, of which we will see many, 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 many. So good.